When de Broglie suggested that particles, as it were real particles, might behave like waves, he realised that demonstrating this would be very problematic indeed. He had come up with an equation which he showed to Einstein, who thought it might sort of be promising. He showed his equation to Einstein, and the equation basically was that the wavelength of a particle, a real particle, would be given by Planck's constant divided by the momentum of the particle. And therefore the momentum is Planck's constant over the wavelength. Now, in this particular question, we've got to work out the momentum, which is p, and the velocity, and we'll get the velocity after we've done the momentum first. Now, working out each of them is very straightforward. First of all, the momentum is h over lambda, and you simply put your numbers in. That's on the data sheet, and that's the wavelength that you've been given. And it's a really small momentum, as you would expect. We're dealing with subatomic and atomic particles. When you know the momentum, you recall that momentum is defined as being the product of the mass and the velocity. So therefore the velocity must be the momentum divided by the mass. The mass of the electron is on the data sheet, and you work out the velocity, and it's pretty fast, 2.3 times 10 to the 7 meters per second. Now, it's very easy to get electrons to go that fast. Electron guns deal with those speeds all the time. But de Broglie knew that really, if his idea was going to catch on, somebody had to actually show the wave properties of an electron. And part B starts the ball rolling as to how you solve the problem. It says that diffraction, now diffraction is a wave property, is the name given to the spreading of the wave after they go through an aperture or an opening. What's the condition for maximum diffraction? And we simply observe that this is the case. The opening or the aperture width has to be the same size as the wavelength. And that means that if you have some plane waves, for example, coming towards an aperture, there's no change in wavelength, no change in speed, nothing like that. It is simply a spreading process. But when these waves, and that is about the same size as that, notice that that wavelength is the same as that wavelength, you get big spreading right the way into the shadow region. So de Broglie, if he was going to demonstrate diffraction of electrons, he had to find a gap about the same size as the wavelength, which was really, really small. Well, 2 years after de Broglie suggested that electrons had wavelengths and could behave like waves, it was demonstrated that they did show the property of diffraction. But where do you get your aperture from? And they realized quite quickly that a crystal might behave like a diffraction grating. So this would be our model of a crystal, nice rows of atoms, and the atoms consist of nuclei with orbiting electrons, and that would be a row of nuclei. There's another row, and they knew that the distance between the rows would be about 10 to the minus 10 meters or so. Now that is not far off the wavelength of, for example, these electrons in this question. 3 times 10 to the 11, and then gaps between layers not far off that at all. So they fired some electrons through this just to see what would happen. And diffraction was seen together with interference. And this is a slightly doctored picture of one. This is the this is the electron tube itself. Electrons come out of the back end, they're accelerated by the anode, and they whack into that screen there, producing a glowing effect, fluorescence. And that's a picture of it. And you get electrons, no electrons, electrons, no electrons, electrons, and so on. So it looks like constructive interference, destructive, constructive, and so on. And if this behaves like a diffraction grating, then presumably the diffraction grating formula should apply. N lambda is d sine theta. And d is the spacing between the layers, and the theta is the diffraction angle. And we're going to see how the speed of the electrons changes the diffraction angle. So this, in fact, is part C. In an experiment, a narrow beam of electrons is directed at a thin metal foil. Now, metal foils are crystalline. And what you've got to describe is what happens to the diffraction pattern when the acceleration voltage is increased. Now, if you make those electrons go faster, their momentum goes up. Now, you may or may not remember that if you make those electrons go faster, the radius of the circle decreases. So we've basically got to try and explain why that happens. Now, if you make the acceleration voltage go up, the velocity of the electrons goes up. Now, what will happen then is that the associated wavelength will go down. Now, the reason for that is that according to de Broglie, the de Broglie wavelength is h over the momentum is mv, and that has gone up. If that goes up, that goes down. Now, if your lambda goes down, the sine theta will go down as well, because n lambda is d sine theta. That's dropped. That hasn't changed, obviously. This will drop. Now, if the sine goes down, so does your angle. And if your angle goes down, you'll find that you don't get the deviation, as it were, of the constructive interference occurring as much. So that radius there will become smaller, and it might come to, say, there, as the diffraction angle decreases. Now, part 2 then goes on to talk about the foil acting like a diffraction grating. What is the effective lines per millimetre if the second order diffraction occurs at 40 degrees? Well, there's your diffraction formula. N is 2, that's the order. The wavelength we're given. And we're going to work out what d is. Now, d is the distance between the layers of atoms. It's going to be the slit separation. There's sine 40, and d comes in as being very, very small indeed, as you would expect. So that basically is about the same size as an atom. So how many of them can you fit into a millimetre? That's what it means when it says the lines per millimetre. How many gaps per millimetre? Well, there's a millimetre. And you say, well, how many of those gaps fit in there? So what would you do? You'd say, well, there's the millimetre. In metres, it's 1 times 10 to the minus 3. And that's the size of one of the gaps. So how many of them are in there? And the answer is a lot. 1.01 times 10 to the 7 of them. And that's the answer that they're after.